When 3 Atlas made its closest approach to Earth, the sky remained quiet. There was no flash, no visual spectacle, and no dramatic moment that the average person would notice. And it is exactly that silence that makes this moment significant. Because even as the object speeds away at tens of kilometers per second, moving irreversibly back toward interstellar space, the data it left behind is only beginning to speak. And what that data reveals does not sit comfortably with what we expected to find. This was never a dangerous encounter. There was no risk of a collision. The object passed at a safe distance of roughly 270 million kilometers. Yet, something about its behavior before, during, and after that passage has shifted, and we are already detecting the consequences. The object may be gone, but whatever event took place did not end when it left Earth behind. The trajectory of 3 Atlas confirms one crucial fact. This object is not coming back. Its orbit is hyperbolic, meaning it is not gravitationally bound to the Sun and will never return to the inner solar system. Once it crosses into the outer regions, it will vanish forever into interstellar space. Typically, that departure marks the start of a slow, predictable decline in activity. As the distance from the Sun grows, thermal energy drops, sublimation slows, and cometary behavior fades. That is the standard model, the curve astronomers expect to see every time. But 3 Atlas is not following that curve. Instead of a smooth fade in brightness, telescopes are recording sudden spikes followed by sharp drops, repeating over and over. This isn't random noise. These fluctuations are coherent, persistent, and, most importantly, synchronized across independent observatories around the globe. Chile sees it, Hawaii sees it, and space-based platforms see it. When different instruments agree, the signal is real. Researchers have begun using an unusual word to describe what they are witnessing, a pulse. Not as a metaphor, but as a measurable, rhythmic fluctuation in brightness and activity that appeared shortly after the Earth flyby and continues as the object recedes. In normal cometary physics, activity decreases after perihelion. The system cools, energy input falls, and behavior stabilizes. Here, the opposite is happening. The object abruptly brightens, dims, and then brightens again in a repeating cycle. The first instinct is to blame rotation, a spinning body with an active region momentarily facing the observer. But the timing, regularity, and stability of these pulses do not fit simple rotation. The data suggests something more complex, a combination of rotation, wobble, and internal imbalance. This implies an internal structure that isn't a uniform block of ice and rock, but something layered, fractured, or unevenly distributed in mass. Here is where the puzzle deepens. Despite the signs of rotational complexity, the jets associated with this activity remain remarkably precise. They do not fan out chaotically or disperse randomly. They are narrow, directional, and repeatable. This is an unusual combination. In natural systems, rotational instability usually produces messy outflows. Precision tends to come from confinement. That confinement could be caused by highly structured emission points or channels that guide material outward in a controlled manner. In known natural objects, strong confinement typically requires deep gravitational wells or significant magnetic fields. A small interstellar body should possess neither at meaningful levels. This doesn't imply anything artificial, but it puts immense pressure on existing natural models. We are witnessing instability and control simultaneously, a pairing that is uncommon in cometary physics. The timing of this behavioral shift is not arbitrary. The pulse began almost exactly when 3 Atlas exited the region where Earth's gravity has its strongest relative influence. This raises a subtle but vital possibility. Earth did not cause the activity, but it may have triggered it. Even weak tidal forces can generate stress in bodies that are fractured, layered, or structurally complex. If the object holds trapped volatile pockets beneath a crust, those stresses could produce episodic releases rather than continuous outgassing. In this scenario, what we are observing is not a new phenomenon, but the latest iteration of a process that may have been activated many times before. near Mars, near Jupiter, or even around other stars millions of years ago. Earth didn't change the object's nature. It may simply have nudged an already sensitive system into a new phase. Once the pulse was confirmed as real, attention shifted inward, because rhythmic behavior almost always points to internal structure. A simple, homogeneous body does not pulse like this. If 3 Atlas were a solid, uniform mix of ice and rock, its brightness variations would track its rotation cleanly and predictably. Instead, the data suggests a system that is dynamically complex, potentially layered or fractured with an uneven mass distribution. That kind of internal architecture allows stresses to build, release, and rebuild in cycles, producing episodic activity rather than a steady decline. The important detail is that this behavior emerged after the Earth flyby, not before, implying the system crossed a threshold. Once triggered, the object didn't settle back into equilibrium. It entered a new regime of behavior that persists as it moves away, which is not what standard post-encounter cooling models predict at the same time. The outflows associated with these pulses remain sharply confined. Gas and dust are not spreading into a broad fan. They're being expelled along narrow, repeatable paths. In natural comet systems, this level of collimation usually breaks down as activity weakens and structural coherence degrades. Here, the opposite is occurring. As the object recedes and overall energy input drops, the directional precision remains. This suggests that the emission points are not random surface fractures, but stable, well-defined channels. Whether those channels are formed by internal layering, compositional boundaries, or long-lived cavities, they imply a degree of organization that is difficult to reconcile with a loosely bound rubble pile. The system appears dynamically unstable on a global level, yet locally constrained where material escapes. Spectroscopic data adds another layer to this picture. The observed ratios of carbon dioxide and methanol relative to water vapor are unusually high, pointing toward formation in an environment far colder than the Kuiper Belt. In such conditions, volatile compounds that would normally be lost early can remain frozen and preserved for billions of years. This alone makes 3 Atlas scientifically valuable, a direct sample of chemistry from another stellar system. But then, nickel enters the story. Emission lines of nickel appear clearly in the coma, while iron, which almost always accompanies nickel, is weak or absent. Separating these two elements at this scale requires unusual chemical pathways. One proposed mechanism involves nickel carbonyl, a volatile compound that can vaporize at relatively low temperatures in carbon monoxide-rich environments. The chemistry is plausible, but has never been observed operating so cleanly in a natural object, and it still doesn't explain why the resulting outflow remains so narrowly focused. Then there is the anti-tail. In standard comet physics, material is pushed away from the sun by radiation pressure and solar wind. Apparent sunward tails can sometimes be explained by viewing geometry, but here, geometry alone does not resolve the observations. The data suggests a physical flow of material moving at least partially toward the sun, resisting forces that should disperse it. Even more striking, that flow is persistent and collimated. Gas expands, dust spreads, narrow streams require shaping. This does not imply an artificial origin, but it demands a shaping mechanism we do not yet fully understand. It is at this point that many existing models begin to strain, not because they are wrong, but because they were never designed to handle an object with this specific combination of chemistry, structure, and dynamical behavior. What is becoming increasingly clear is that whatever changed during the Earth passage did not simply fade away once the object moved on. The pulsing behavior continues as 3 Atlas recedes, which implies the system has shifted into a new operational state rather than experiencing a brief disturbance. In physical terms, this suggests a threshold was crossed. Once internal stresses were released or internal pathways were opened, the object did not reseal or stabilize. Instead, it settled into a repeating cycle, like a mechanical system that has slipped into resonance. Natural bodies can do this, but it usually requires a very specific internal configuration, one that stores energy and releases it periodically. The persistence of the signal tells us this is not a transient flare, but an ongoing process that Earth's gravitational influence is weak compared to the Sun's. But weak does not mean irrelevant. For a body that is fractured, layered, or internally complex, even small tidal gradients can act as a catalyst. The timing strongly suggests that the object's exit from Earth's zone of strongest relative influence coincides with the onset of the pulsing behavior. This doesn't mean Earth caused the activity in a direct sense, but it may have acted like the final tap on an already stressed structure. In this context, Earth becomes part of a longer chain of interactions, one that may have included close passes by other planets or stars long before this object ever entered our solar system. What we are observing now could be the cumulative result of repeated tidal interactions over millions of years. As more data is analyzed, it becomes harder to fit 3 Atlas into existing cometary models without extensive modification. Standard models assume relatively simple internal structures, gradual thermal responses, and predictable post-perihelion behavior. Here, we see abrupt changes, rhythmic activity, precise outflows, and chemical signatures that diverge sharply from expectations. Each anomaly can be explained in isolation with enough assumptions. But when combined, those assumptions begin to pile up. This is often a sign that the model itself is incomplete. Not wrong, but built for a narrower class of objects. Interstellar bodies formed in environments we've never directly sampled may simply fall outside the comfort zone of those frameworks. Beyond the specifics of this object, 3 Atlas is forcing a larger realization. Interstellar objects are not just fast-moving curiosities that briefly pass through and leave. They can be chemically rich, dynamically active, and structurally complex even after leaving the region of strongest solar influence. The fact that this object was discovered relatively late in its approach highlights how easily such visitors can slip past our detection systems. If 3 Atlas had been slightly smaller, darker, or faster, none of this data would exist. The implications extend beyond this single case, suggesting that the galaxy is not a quiet backdrop, but an active environment through which material regularly moves, interacts, and occasionally surprises us. Point one detail that keeps resurfacing in the data is coherence. The pulse is not drifting, decaying, or desynchronizing as the object moves farther from Earth and the Sun. Instead, it remains remarkably stable in both timing and amplitude. In astrophysical systems, coherence over time is difficult to maintain without an underlying structure enforcing it. Random outgassing produces noise. Thermal relaxation produces smooth curves. What we are seeing instead is a repeating pattern that survives changing external conditions. That tells us the driver of this behavior is internal, not environmental. The object is not reacting passively to its surroundings anymore. It is operating according to its own internal dynamics, and that alone makes it an outlier among known cometary bodies. The pulse has also allowed researchers to infer aspects of the object's rotation that were previously inaccessible. The data does not support a simple spin around a single stable axis. Instead, it points toward a combination of rotation and wobble, a complex motion that implies uneven mass distribution. This is exactly what you would expect if the interior were layered, fractured, or contained cavities of differing density. Such internal heterogeneity would explain why stresses accumulate and release episodically rather than continuously. Importantly, this kind of structure would also allow channels to remain stable even as the bulk motion of the object becomes irregular, resolving the apparent contradiction between global instability and local precision in the jets. Another implication of the current behavior is memory. Physical memory, not conscious, but structural. The object appears to respond not just to present conditions, but to accumulated history. If tidal interactions during the Earth flyby were sufficient to trigger this new phase, then similar interactions in the past may have left lasting imprints. Closed passages near other planets, near its parent star, or even through dense interstellar environments, could have progressively shaped its internal architecture. What we are observing now may be the final expression of a long evolutionary process, one that began long before this object ever entered our solar system. In that sense, 3 Atlas is not just passing through space. It is carrying a record of every significant gravitational interaction it has ever experienced. Perhaps the most unsettling aspect of this phase is that the object is leaving while still active. Most comets quiet down as they retreat, becoming observationally uninteresting long before they disappear from view. 3 Atlas is doing the opposite. Its most intriguing behavior is emerging late, after the closest encounter, after the moment when attention usually fades. This inversion of expectations means we are watching a system evolve in reverse, becoming more complex as it exits rather than simpler. In observational astronomy, that is a dangerous situation because it means the most important data may arrive when the object is already becoming too faint to study in detail. The clock is running, and every new pulse detected is a reminder that whatever changed did not end with the Earth flyby. This distance from the Sun. The rules should be simple. Less energy in means less activity out. Thermal models are very clear on this point. As an object recedes, sublimation weakens, jets soften, and variability smooths out. But 3 Atlas is refusing to cooperate with that logic. The pulse does not weaken in a clean exponential decay. Instead, it maintains a structured rhythm, suggesting that thermal input is no longer the primary driver. This implies that the system has become internally regulated, meaning the energy source controlling the activity is at least partially decoupled from direct solar heating. That does not require an exotic explanation, but it does require a rethinking of how energy can be stored and released inside small interstellar bodies. Another striking feature is endurance. The channels guiding material outward do not collapse as activity continues. In fragile cometary nuclei, sustained outgassing usually widens vents, erodes structure, and leads to a progressive loss of definition. Here, the opposite appears to be happening. The jets remain narrow and repeatable over time, implying that the pathways confining the flow are mechanically robust. This suggests a material strength higher than expected or a geometry that naturally reinforces itself under stress. Either way, it challenges the idea that this object is a loosely bound aggregate. Whatever its internal makeup, it behaves as if it possesses architectural integrity even while undergoing dynamic internal changes. The regularity of the pulse hints at resonance. In physics, resonance occurs when a system naturally oscillates at a preferred frequency due to its structure and energy distribution. Once excited, that oscillation can persist with minimal external input. The Earth flyby may have provided the initial excitation, but the persistence suggests the object has an internal configuration that supports sustained oscillation. This is not something we typically associate with cometary bodies, which are usually damped systems that lose energy quickly. Resonant behavior implies compartments, boundaries, and feedback mechanisms, all hallmarks of structural complexity. Again, this does not point to intent, but it does point to organization as these behaviors accumulate. A gap opens between what we observe and what we can comfortably explain. That gap is not a failure of science, it is the beginning of it. The continued monitoring, the extension of observation windows, and the reanalysis of earlier data all signal that the scientific community recognizes this tension. When an object forces multiple models to stretch at once, it becomes a priority case. Not because it is mysterious in a sensational sense, but because it exposes blind spots. 3 Atlas is doing exactly that. It is not loudly announcing its nature. It is quietly insisting that our assumptions about interstellar objects may be incomplete. This is where the story truly lands. Not with certainty, but with tension. 3 Atlas passed Earth quietly, without spectacle, without danger, and without drawing attention from anyone who wasn't already watching closely. Yet after that moment, something changed. An object that should have been fading instead began to pulse. An object that should have been cooling instead showed structured, rhythmic activity. An object that should have behaved like a standard comet instead revealed internal complexity, chemical signatures, and directional precision that strained the limits of our current models. Nothing in the data requires an artificial explanation, and pretending otherwise would miss the point entirely. The real significance of 3 Atlas is not that it proves something extraordinary, but that it exposes how narrow our expectations have been. Our models are built almost exclusively on objects that formed here in one solar system, under one set of conditions. This object did not form here. It arrived carrying a history shaped around another star, possibly over millions or billions of years. And now, it is leaving before we can fully decode that history. What we are seeing after the Earth flyby is likely not a new phenomenon, but a delayed revelation. A system pushed past a threshold, settling into a mode of behavior that reveals its internal architecture rather than hiding it. Pulses instead of decay, precision instead of chaos, activity that persists even as the object retreats into the cold. These are not violations of physics, but reminders that physics can play out in ways we have not yet cataloged when the initial conditions are unfamiliar. 3 Atlas is already on its way out. Its orbit guarantees there will be no second encounter, no easy follow-up years from now. Soon, it will become too faint to study in detail, and eventually, it will vanish completely into interstellar space. What will remain are the records, the light curves, the spectra, the timing of those pulses, and the uncomfortable questions they raise. Was this an extreme natural case? Almost certainly. Was it normal? Clearly not. And that distinction matters. Science advances not when everything fits, but when something refuses to. 3 Atlas has done exactly that. It has forced us to confront the limits of our assumptions, the gaps in our detection capabilities, and the reality that the galaxy is not a quiet place filled only with familiar debris. Interstellar objects are out there, passing through more often than we once believed, and some of them will not behave the way we expect. If you want to stay updated as new data comes in, and as future interstellar visitors challenge our understanding even further, make sure you're subscribed, because the next object like this may not announce itself clearly either. And by the time we realize what we're looking at, it may already be on its way out again.